Okay, 10-minute break. So I'm here. You can ask any question you want. Do you guys have any questions so far? Hello? I think our break time is over.
Yeah.
So do you have any questions so far? Going to the next step, we you should ensure that you do not have any other question. Is everyone here?
Yes.
I'm here.
Yeah.
Yes.
Yeah.
Okay, I think I can start, right? Dr. Friedberg is not here yet. Just wait for 2 more minutes. Like, so far you can follow, right?
Yeah.
Yeah.
Okay. This kind of stuff, like these are a little bit theoretical. It'll become clearer when we do some problems. We can solve some problems, then it'll become clearer. I'm planning to like complete the theory today. So after this, we'll talk about Hamiltonian and Hamilton-Jacobi theory. Then we'll solve problems for like one problem for all. Okay, I think we should start now. Okay. We are trying to show that variation of S, when S is defined as integral of Lagrangian, variation of S equals to 0 if F equal ma holds. So we are going to consider F equal ma as our starting point, and we will prove variation of S to be 0. So F equal ma for a conservative force field, if F equal ma can be written as, force can be written as negative derivative of some potential, right? When u is just a function of position and most position only, not time.
Yes.
Okay, so we are going to consider this thing to be true, that m d to r, r is position of the particle, position vector of the particle we are talking about, equals to negative derivative of potential, this. Or if this thing equals to true, then m d to r over dt squared plus gradient of u equals to 0 as well, right? We are going to consider this thing to be true. So let's start with the definition of S. So consider a particle from starting to final point, it moves through a curve that is this. So any point on the curve is probably this one, this point is denoted as the position vector r, and this is the right path. So we need to consider a varied path a little bit. So if we vary this path, probably this becomes this infinitesimal variation, not a lot. So this thing. So say when we vary this path, this point becomes that point. We denote it by big R. So small r and big R are separated by infinitesimally, which means big R, the varied path, which is a function of time, equals to actual path that particle took is r at t plus some infinitesimal vector, this vector, like separation vector between these 2 points, which is also a function of time, like that. All we need to do, we need to consider Lagrangian for this one, Lagrangian for that one, Lagrangian for that one, and construct action for this one, action for this one, and take the separation between those two, right?
Yes.
Okay, great. So Lagrangian Lagrangian for the correct path, Lagrangian for the correct path would be function of r, time derivative of r, and most possibly time itself. And Lagrangian for the varied path would be L of big R dot, and most possibly time itself. So the change in action delta S would be, let's call it a different notation like L naught and S naught, then we can distinguish. So L naught is like the Lagrangian through that original path, and L is the varied path. So also the corresponding variation would be like S, like the action through the varied path, which is a functional of big R, minus S, which is a functional of S naught, which is a functional of R, right?
Yes.
Yeah.
So then we can write S equals to S of R, S functional of R equals to T1 up to integration T1 up to T2 Lagrangian, whatever it is, Lagrangian evaluated at evaluated through R, right, dt minus sorry, it's function, not functional. So R dot, and most possibly time. So do you agree up to this point?
Yes.
Okay, so all we need to evaluate the L for both of the path. So the standard prescription of Lagrangian is kinetic energy minus potential energy, right? T minus V. So the T would be like T at L would be kinetic energy at like the, so that would be half m big R dot squared, which means big R dot bigger. That means this thing, right?
Actually, how do we know that Lagrangian would be T minus V?
That's the standard prescription.
Yeah, but how do we know?
From previous class, I think.
Yes, from previous class. We defined our Lagrangian to be that.
Okay. Then why does it work? Actually?
What do you mean? Why does it work?
For example, Lagrangian could be any other value. For example, T plus V square or something like that. But why it
Yes.
is T minus V?
Oh, T minus V is the standard prescription. We know at least this thing works.
Okay.
So instead of like, the better question would be, how do you define your action? Our action is defined to be integral of T minus V dt.
Okay.
We are just calling it Lagrangian, T minus V to be Lagrangian. That's all. But that depends on very definition of S itself here. Okay, so half m r dot minus minus V, or we call it potential, so U of R, like that. It could be like in principle depend on T as well. It's actually not a concern for R. It could be. So okay, This is L. So what would be our L naught? L naught would be T naught, like the kinetic energy through the original path, minus V naught, the potential energy through the original path. So that would be half M r vector dot r vector dot minus U evaluated at small rt. Do you agree?
Yes.
Okay, great. Now we can actually, for big L, we perform a Taylor big L, we can perform a Taylor expansion. So we can write half M, instead of r dot, we actually replaced by smaller sorry, smaller plus epsilon. So we can write smaller dot plus epsilon dot smaller dot plus epsilon dot, like that. Here, minus U of smaller plus epsilon comma T, like that. We can write like that. Okay.
Yes.
So remember, epsilon is a really small or infinitesimally small vector. So we can take dot. We can evaluate the dot product and write half M r dot r dot plus half M multiplied by twice r dot epsilon dot plus half M epsilon dot epsilon dot.
Yes.
Okay, and for Taylor expansion, for U we can write negative. What do we write here? U at r comma t plus
Partial of
epsilon dot
Derivative.
gradient U of RT plus dot dot dot, like that, where dot 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 means higher order of epsilon. So we actually neglect or dump a second order of epsilon into just one function, one term. So we end up having half M r dot r dot plus M epsilon dot r dot minus U of RT minus epsilon dot grad of U, and then finally plus order of epsilon squared. That means higher order terms that we can neglect.
Yes.
So from this line, actually, we could see one more thing as well. So we could write these two terms like variation of S.
Oh, well, epsilon is infinitesimal, but epsilon dot would be
Yeah, that's a very good question. So epsilon dot could be anything like it could be non-infinitesimal, right?
yeah.
So it could be something big. So if something big, like rate of change of E would, like rate of change of R at that point would be big. So that, like after that point, so like adding that, like if E changes fast, then at the next point, like the difference between those R and R bigger, smaller and bigger would be big. So we are demanding smaller and big R are infinitesimally separated everywhere, that gives this condition. So epsilon remains small everywhere. So obviously then epsilon cannot change that too fast.
Okay.
Can you refresh it, please? I didn't get that.
So okay, let's see the diagram. So here epsilon is small. Every point is epsilon is small, not just one point. So if epsilon dot is big, then epsilon would change fast, right? Then here it might be small, but after some like integration over this t, it could be like big, like this. So we are demanding epsilon remains small for every point. So obviously epsilon dot has to be small as well. Otherwise it won't.
Got it.
Okay. So basically the variation of S is basically L minus L naught integrated over T, right? Right? L minus L naught. So that's why we take the separation between L and L naught. So L minus L naught would be what? So L naught had like half M R dot dot R dot. So this term and that term, they match. So they cancel out, right?
Yes.
So leading order term would be M epsilon dot R dot. Also, this term and that term match, right? So they cancel out. So the leading order term would be negative epsilon dot gradient U plus order of epsilon squared. That would be the separation, right?
Yes.
Okay, great. Now we substitute that L minus L naught inside of that variation. So variation of S, change in S would be T1 up to T2, integration over this M epsilon dot R dot minus epsilon dot grad U plus, we are neglecting this higher order term dt. So leave this term as it is, but integrate this term by integration by parts. So if you do that, integrate epsilon, so it gives you M R dot epsilon vector evaluated at T1 to T2, right? Minus M integration T1 up to T2. Now you integrated epsilon, so now you have to differentiate R dot. So it gives you R double dot epsilon dt, and then negative integration T1 up to T2 epsilon dot grad U, right? So what is epsilon at T1 and what is epsilon at T2?
It will be 0.
It has to be 0 because epsilon otherwise
Capital R
like
is equal to small r
yes,
in the boundary.
at the boundary, right? So this term goes away. So finally we end up having negative, or negative integration T1 up to T2 M R double dot plus gradient of U dot epsilon dt, right?
Yes.
But from Newton's law, we know this thing is 0, right?
Yes.
So that's why what we substitute here. So if you substitute 0 over there, that gives you 0. So we have now variation of S to be 0, when you imposed Newton's law. So this is equivalent to Newton's law.
Yeah.
At least in mechanical case. Okay, so now we have full confidence on our like formalism. So this principle, this variation of S to be 0, this principle is known as Hamilton's principle, and this is considered the fundamental of all mechanics. Hamilton's principle. Okay.
Yes.
Okay. So mother of all mechanics is now variation of S equals to 0. So it has one possible formalism as Newton's law. So which says F equals to mr double dot, right? One possible is Lagrange's equation or Lagrangian mechanics. Lagrange's equation. So which says delta L over delta coordinate equals to ddt of delta L over delta q dot. Question is, can we generate more?
Yes.
Yes. Answer is yes. We can generate more. So we'll see that later. First, we analyze some properties of Lagrange's equation and use it somewhere at least. Then we'll see. I'm not sure what problem we can solve here. Like we can explicitly do. Can you suggest one? I can do that.
Actually, we can find out the distance between 2 points on a plane.
So no, that's mechanics. That's not that.
Okay,
I'm talking about mechanics. Give me a mechanical problem.
Okay.
So yeah,
maybe a pendulum problem.
Yeah, a pendulum problem is a great one. Okay, so for pendulum,
up to double pendulum.
No, not double pendulum, single pendulum. So what's the point of doing double pendulum? It doesn't, if it doesn't show anything that we already know. So for pendulum, instead of having a Cartesian coordinate like xy, we could use our polar coordinate, right? Like r, yes, and angle like phi. So in this formalism, all we need to find what? First, we need to find kinetic energy, right? T.
Yes.
So remember, whenever you do not know what's the form of kinetic energy in that coordinate, you just start with Cartesian one, because in Cartesian coordinate, you know the precise form of kinetic energy. So if this object, this bob has a mass m, then kinetic energy of that object would be half m x dot squared plus y dot squared in Cartesian coordinate. So now we need to change this thing into polar one, right? So we need to find the relation between r and like r phi and xy. So if we consider like this thing to be our origin, like origin of x comma y coordinate, this is the origin. So what would be the relation between those two?
X equal to r cos phi and
no, you cannot write that. So it depends which is your x-axis and which is your y-axis. So tell me which one I can.
We consider the vertical axis as y and the horizontal axis as x.
So this is your y and this is your x.
Yeah. Then
so you want to do the opposite way, that I understand better. So I want to do this one as my y.
Yeah. Okay.
Okay, great. Then so question is, how much is here? What is the x value over here?
Here x equal to r sin phi.
X equals to
r sin phi.
Are you sure?
Yeah.
X equals r sine phi. And then
Y equal to minus r cos phi.
y equals to minus r cosine phi. Is that correct?
Yeah.
Okay, great. Now, for this pendulum, we know r is a constant, r equals to L, right? So we can actually write L sine phi, L cosine phi. So we have our x dot equals to L cosine phi, phi dot. And for y dot, we have L sine phi, phi dot. So if you square those things and add those two up, then you get L phi squared, phi dot squared, L squared, phi dot squared, or L phi dot whole squared, like that.
Yeah.
Yes.
Because it has cosine squared, it has sine squared, then it just becomes 1. You're left with L square and phi dot square. So this is the form of kinetic energy here. But if you had a system that was r was varying, then it would be a little bit different. Remember, you have to be careful about that. So okay, so what's the potential energy now in terms of y coordinates? So what is the potential energy? mg1.
Yes.
So what would be that? mg. What was y?
Here, this is
L?
tough actually. I can say
No,
mg
no, no, it's not tough. It's not
h or
tough.
something.
Just substitute. Y. What is y? I
Oh,
consider my y.
yeah.
So
You can do anything.
valid potential energy.
It's L cosine phi. Okay.
Y was negative L cosine phi, right?
Yeah.
So that's why we what we get. So now our Lagrangian would be T minus V, that is half M L squared phi dot squared, then plus mg L cosine phi.
Yeah.
Yes.
Right? So now we have to find like delta L over delta phi. What's that?
It's minus mgl sine phi.
Minus mgl sine phi. Okay, right. Then ddt, okay, not ddt, I just write the other part. Delta L over delta phi dot, what's that?
ml square phi dot.
M L squared phi dot. Right. So our Lagrange's equation says negative mgl sine phi equals to ml squared phi double dot.
Yeah.
So we all know this is our equation of pendulum, right?
Yes.
Hmm?
Yes.
So we can actually
Yeah.
cancel out this L and M. So we end up having more familiar form, that is x double dot plus g over L sine phi equals to 0.
Yeah.
This is the more known form. Okay, so we got our equation, equation of motion, differential equation of motion. But point is, Lagrangian mechanics, it doesn't help. Like Lagrangian formalism doesn't help us solving the differential equation itself. We would still need to go through the same difficulty of solving this differential equation as we had in Newtonian mechanics.
Yeah.
Right?
And it's very tough to solve this one due to the sign.
Yes, it's a little bit difficult. It's not that difficult. It's a little bit difficult because it's a non-linear differential equation, and in general we do not know what does that mean, how to solve it. So that's why it's difficult. But we'll boil it down later. So okay. So far so good. Do you have any questions so far? Basically, we know that to produce differential equation, like differential equation of motion, Lagrangian procedure helps. That's all. But it doesn't help us to solve the differential equation itself. But to find equation, like to find the motion, we actually need to solve this differential equation. So that's one of the biggest hurdle. Okay, so this is one thing. Now we actually proceed to go in another direction. First, we know the Noether's theorem in classical mechanics. Noether's theorem in classical mechanics. I think I have few more minutes before the break, so I think I can utilize it properly. Okay. So we have our action to be this, right?
Yes.
Also, we know the equation of motion is generated by variation of s equals to 0.
Yes.
So we know we have a coordinate system q. When you change the coordinate system a little bit, you make this thing, the L remains same. Then your action remains same. Then it's automatically satisfied. Right?
Yes.
Our claim is when this thing happens, when your Lagrangian is unchanged under a coordinate transformation, there exists a conserved quantity.
Yes.
So there is some quantity that is unchanged over this coordinate transformation. That is our claim.
Yes.
So when we change our coordinate q to variation of q, we can write variation in like change in L. It's not variation, it's change in L is basically delta L over delta q, change in q plus delta L over delta q dot, change in q dot. Obviously, if you have multiple coordinates, then you have to write the indices as well, like this. And remember, when I write this repeated indices, it means like there is a sum over I as well.
Yes.
Okay. Also, we know one more thing, that variation is unchanged by adding a number here, right? Like variation is changed, that's true, but variation of S produces the same equation of motion, right?
Yes.
So at max, we can demand that this variation of L, like changing L, if this is equals to some quantity that is f is a function of q and t only, if we can satisfy this thing, then there is a conserved quantity. That's the more general version. So okay, so let's proceed with this. What is delta L over delta q using Lagrange's equation?
It is general. Okay. Generalized force.
No. But use equation of motion. Use the Lagrange's equation of motion here.
Oh, well, I have a question.
Yes.
In the proofs, we didn't use the fact that Lagrangian can be explicitly depend on time.
Oh, you can do that, but we are actually changing only one coordinate, not time. Time is fixed.
Oh, well, we can see time invariance too. So
Yeah, in another way, yeah. So by direct procedure here, we do not do that. We are only talking about coordinate transformation.
okay.
So that's another way we are going to see that. So like coordinate and like spatial coordinate and temporal coordinate, those are two things. So we do those things differently. In mechanical case, those are different.
Okay.
Okay, so use Lagrange's equation here. What is delta L over delta Qi? Use Lagrange's equation.
This is d dt of
ddt of delta L over delta Qi dot,
yeah.
right?
Yeah.
Also, we can write this thing as well. We are dealing this side only first. So we can write this thing as, by product rule, we can write this thing, ddt of delta L over delta Qi dot multiplied by variation of Qi.
Yes.
This, yeah, this thing has to be satisfied with the other side, which is df over dt. So it implies that we can write ddt of delta L over delta Qi dot variation over Qi minus f equals to 0, which implies by integrating over time, it gives delta L over delta Qi dot variation Qi minus f equals to 0. Oh, sorry, not 0.
Any constant.
Or big C. So if you can satisfy this thing, if you can find a coordinate transformation, that can be written as total time derivative of some f, then you always have a conserved quantity in your system. That's the point. If you have a coordinate transformation for which your Lagrangian can be, change in Lagrangian can be written as total time derivative of something, then then you can always find a conserved quantity in your system. Happy?
Yes.
Okay, we'll see some example over here. Also remember, f has to be an infinitesimal quantity. So we actually write like this: f equals to delta g over delta q variation q, like that. So if you can find some g which satisfies this also helps. Same thing. So if you substitute this thing over there, it gives you delta L over delta Qi dot minus delta G over delta Qi variation Qi equals to C. So variation Qi is an arbitrary constant, so the object inside of it is a constant.
Yes.
Okay, so let's see some examples, then we'll understand what we mean. So you are given with a Lagrangian when we know that momentum is conserved, like consider a freely moving particle in x-axis. So for that thing, the Lagrangian would be half m x dot squared. Agree?
Yes. Yes.
So let's see if we have a conserved quantity. We know the momentum is conserved here, or x dot is conserved, right?
Yes.
So let's see that thing can be found from here. So let's change our coordinate. So x prime, like new coordinate, x becomes x prime equals to the old coordinate plus infinitesimal quantity a. That means our variation of x equals to a, right?
Yes.
So what would be our delta L? change in L. Change in L is by chain rule we know delta L over delta X, variation over Xi, variation of X plus delta L over delta X dot variation X dot, right?
Yes.
So delta L over delta X, what's that?
This is 0 here.
0. So we are left with the only other part. So that is delta L over delta X dot. What's that?
This is mx double dot.
mx dot. mx
Mx dot. Mx dot.
Mx dot.
What is variation of X dot?
Variation of x dot.
0.
A is constant here.
Hmm?
Is A is constant here, the infinitesimal quantity A.
Oops. Actually, I should have done another line actually here. So all I need like the it's a parameter. It's a very variable, like it's a constant parameter. So yeah, actually I should have applied another thing, not this one. We already calculated the other one, like delta L is ddt of something. This is what I wanted to write. Ddt of delta L over delta X dot variation of X. This is what I wanted to write.
Yes.
This is what this is the thing I wanted to write. So all we need to find some f for which this thing is satisfied. Delta f over delta df over dt. This thing is satisfied, right? We want to find an f. So substitute that L over there, delta L over delta X dot. What's that? This is mx dot. So we want something that some f for which this thing is satisfied, that delta L over delta X dot change in X minus f of which ddt of that thing equals to 0. So this is I want to satisfy. So substitute it over here, we get mx dot and variation of x is give you a minus for some f we want this, right? So for some f we want to satisfy this one. So that's the goal.
Yes.
Okay, so for which f this thing can be satisfied? Any constant, right?
Yeah.
We can set f to be a constant, any constant. So let's set f to be a constant. Basically it's pretty trivial, that's why you cannot see many things. So this part becomes 0, so ddt of this inside of this thing automatically gives you a like conserved quantity. So your conserved quantity j equals to m x dot multiplied by some a, which is a parameter, minus c. So you can write in principle like to be I want to show this part to be conserved. So actually I divide everything by a, which is a constant parameter. So j by a equals to mx dot minus c by a equals to some d. So d is also a constant, so it gives me mx dot equals to j by a minus d. According to construction, this whole thing is constant, right? So mx dot has to be constant. It's pretty trivial, so that's why you cannot see many things. So we can do a little bit complicated thing that might seem doesn't have a conserved quantity, but it has. Then you'll understand. So okay, let's see. Then you'll understand. So question is, if my Lagrangian is half m z dot square minus mgz, like a falling object, what thing is conserved?
Well, can you repeat the question again?
So if you release an object
Energy.
from,
The total energy is conserved.
okay, energy, like energy is conserved, but the energy conservation is not included here.
Okay.
We are actually talking about momentum conserved.
Yeah.
Conserved.
Yeah.
So what is that momentum that is conserved?
Angular momentum.
It's a point particle. Yeah,
Okay.
angular momentum is conserved. That's true as well. There is a linear momentum. There exists a linear momentum that is conserved as well. So
Yeah,
that's
it's other
Y
coordinate.
component or X component.
okay. Yeah, those are conserved as well. But when we wrote like L equals to half m z dot square, then we are not considering the other coordinates as well. Like there is no x and y.
Yeah. But if I change the coordinate system, then I can.
Let's see. Can we find one? Can we find one? Can we find a conserved quantity? That's the question. So let's change our z to be z prime, that is z plus a. So obviously our z like delta z equals to some a, and obviously which means delta z dot is basically 0. That's true as well. Okay, but let's substitute the thing, like let's find the change. So what is delta L? What is delta L? Delta L is obviously delta L over delta Z, variation of Z, plus delta L over delta Z dot, variation Z dot. If we substitute everything, what do we get? What is delta L by delta Z?
This is minus mg.
This is minus mg
And
A.
times delta z. Oh yeah. A.
So question is, can we write this part equals to ddt of something?
mgat.
Yes, exactly. Negative mgat.
Yeah.
We can write this thing as negative mgat. So if we choose our f to be negative mgat, then our conserved quantity is like j equals to this part. So conserved quantity is like delta L by delta Z dot, variation Z minus F. This is our conserved quantity, right? So this is equals to negative mga, mga, oh, no, it's not g, it's delta L by delta Z dot. Sorry, it's positive as well, right? So it's mz dot, and what is variation Z? It's a. And what is F?
If is
Minus mgat.
Yes. So divide whole thing by a. So this is our conserved momentum, P equals to j by a, which is mz dot plus mgt. This thing is constant. This is a conserved quantity of motion. Neat, right?
yes.
So even you're seeing that yes, everything is moving, there is a conserved quantity, but that conserved quantity may have an explicit time dependence, that's all. But total time derivative of that thing is 0.
Yeah.
Okay, so this is what the Noether theorem was. It says that whenever you have a concept or whenever you have a symmetry in your Lagrangian, you can always find a conserved quantity of motion.
It is basically the initial velocity, right?
Yes.
Initial
Yes.
momentum. Yeah.
It's the initial momentum. Yeah. Actually, when we do Hamilton-Jacobi theory, we'll see that basically we'll try to find a transformation between those initial coordinate and momentum to our coordinate momentum at x.
So we are considering the field as our system here. Are we considering this field as our system?
What field?
Gravitational field?
No. Our system is that mass that moving inside of that gravitational field.
Okay.
Okay, so we'll see this. It has actually much more general application. Like even there is a motion, we can find a conserved quantity, and that's basically the initial quantities.
Yes.
So if we can find like we are actually trying to find coordinate and momentum as a function of time. Say we have coordinate and moment as a function of time, but we can find a transformation relation that converts those things into like Q naught and P naught, those initial data. Then we have a relation between the like initial data and data at time t. So that's basically the solution as well. So this is kind of the generating function S. We'll see in later time. Okay, let's take a break and come back within 5 more minutes. Like,
But can you please repeat the last sentence again? Yes.
so
Sorry.
in the last line I said like we'll try to find a transformation relation between initial coordinate momentum to a coordinate momentum at time t.
Oh,
That's basically the solution of the system as well.
yeah.
And that actually hidden inside of this F. So we need to find a procedure to finding this F. That's all.
Yes, this is interesting.
Okay, let's take a break. It's 11:10 a.m. here, so we'll come back at 11:15 a.m. like within 5 minutes.